All right, good morning, chemists. This is lecture 10 of your favorite course, Chemistry 132B. This is the last lecture before the midterm on Friday. I'd like to point out that I have posted the supporting information for the practice quiz, which is present on the class website, so please check that out. I will also post the key for the worksheet for this week right after this presentation. So hopefully that will be sufficient for you to prepare for the exam. There was a question here in the chat box about whether the lectures 1 to 10, because that is the material for the midterm. Lectures 1 to 10 corresponds to chapter 7 in the book, in the Atkins book. Okay, so it's basically chapter 7 of the book, although the book, again, is more for a reference for you rather than the primary source of information. Okay, so please understand that. Not everything in the book we covered exactly in the course, and some things in the course go beyond what's written in the book. So the book is useful to just to read up on the information, but don't take it as a primary source of the material. So with that, I will just cover the last part, that is part of the midterm, although I have to emphasize that today's lecture will not be a major part of the midterm, okay? But I will basically lay out this information anyway today, because that will conclude chapter 7, it will conclude the first part of our course, and after the midterm, we will move on with something more specific, which is the hydrogen atom. So after the midterm, that is what we will be talking about. And before the midterm, I'd like to wrap up everything that we would call the principles and basics of quantum mechanics. So what is the part that we haven't talked about yet? Okay, so that is due today. And let me start with what we talked about on Monday, which is the motion of a particle on a ring. And here is the drawing once again. You see here the particle in green, it's moving along in a circle, and it has a distance r relative to the axis z. So it spins around the z-axis. I can now write a p, that is a vector p, which is the momentum, the angular momentum, if you wish. And that's what it's going to be. But right now, the p is pointing in one direction, which is tangential to the circle, as you can see. So that will be the linear momentum at that particular time point. Okay, so the angular momentum is defined as follows. It is written as L, okay? L equals R, which is the vector R, and then the vector product with P, okay? So P is the linear momentum indicated by the red arrow. Now, it is a vector product, so these things have direction. The vector R has direction, goes from the origin to the particle. The vector P has direction, it is tangential to the motion on the ring. And so where does L sit in this frame? And that is, of course, done by the right-hand rule. Maybe you remember that. Here it is. So in this case, vectors A and B. A is R, P is B here. So it's R, and then vector product P, and that will be the new vector C here, which is now L. So L will point up here. There it is. Okay, so that is L. I call it LZ because basically it is the angular momentum that's projected along the z-axis. So if a particle spins around the z-axis, then its angular momentum is pointing up if the particle spins counterclockwise, okay, as you can see here. So that is the angular momentum of this particle. There's nothing quantum mechanical about this. This is the same in classical mechanics, okay? There's nothing mysterious about this. If you have taken physics courses, this is something you probably have seen before. Now, we can compute this this angular momentum by doing the vector product, and that's indicated over here. R, of course, is x, y, z, okay, and p, px, py, pz, and then I, j, and k are the vectors, the unit vectors along x, y, and z. Now, we are interested in the LZ component, the component directed along the z-axis, okay, so that is the k points along z. How do I calculate that component? Well, what I do is, of course, is I take x and then times py minus y times px, okay? So that's taking the vector product for one of the components, it's going to be LZ, that part along Z, that is the part along K with a little roof on it, little head on it. And so what I find is X Py minus Y Px. That's basically the components right here in the vector product. So the component along the Z-axis, the angular momentum component, is written as such. So that is classical, okay? Again, there's nothing quantum mechanical about this. This is true quantum mechanics-wise. It's also true classical-wise. So how do we make this a quantum mechanical angular momentum? Well, by taking the operator version of this. So LZ now is an operator. It has a little hat, and the X is the position operator. The Py is the momentum operator in the Y direction. And then the Y with a little hat is, of course, the position operator in the Y dimension. Okay, so this is the one way for me to convert it from a classical expression to a quantum mechanical expression. Now, I have actually, explicit formulas for these momenta, because I know that I can write a momentum as h bar over I, and then a derivative with respect to the coordinate, which in this case is py, that means the derivative to y, and for px, the derivative to x. Okay, so these two here, these components, is the momenta along y and x, and the x and the y, of course, are the position operators, which is just multiplication by x and multiplication by y. Okay, so this would be a quantum mechanical version in operator form of the angular momentum along the z-axis. Okay, so how do I clean up this whole thing a little bit? Because what I really want, I want it in terms of r and the angle phi. So how do I do that? You can do that. It's not so hard. Okay, you can convert that, and it turns out if you do that, and I've written that out in the notes, in the lecture notes of lecture 9, actually, you can look that up. You can see that this expression above can be reduced to the expression below it. H bar over I, and then the derivative with respect to phi. Okay, so there's no r dependence in here. It's only dependent on phi. So basically, it's the first order derivative with respect to phi. That would be the angular momentum in this system. So what does that mean for us? Because last time, what we found are functions that look like this. Okay, I had this function, big capital phi, as a function of the variable little phi, where the little phi, of course, is going to be that angle. Okay, and it had a normalization constant, which we determined last time, but for now I'm just calling it n, and then I, ml, and then phi. Okay, so this is the shape of the functional shape of the wave function that we solved through the Schrödinger equation. So the phi here will go spin in this direction. So this will be a particle moving along this track. Okay, so this will be a wave function describing the unidirectional motion of the green particle along the ring if it spins counterclockwise. So what would be the angular momentum operator operating on this wave function? Okay, so what would be the eigenvalue of this wave function? Does it have an eigenvalue? Is it an eigenfunction of this operator LZ? So let's find out. We just have to take the derivative with respect to phi. Okay, so let's do that. I'm going to take the derivative with respect to phi of this function. This is the function once again, ml, and then phi. And I see that I can do that quite easily, just derivative of this exponential function. That's going to be I, ml, and then times this constant once again, h bar over I, and then the function again. Okay, so that's definitely an eigenfunction because I can write it as this I can cross out, this I crosses out, so I simply get ml h bar and then times the function again. Okay, so that basically means that yes, this function we found by solving the Schrödinger equation for the particle on the ring is also an eigenfunction of this operator, the angular momentum operator, with its projection along z, and the eigenvalue is ml h bar. So the magnitude of this arrow, is ml h bar. So depending on what ml is, the quantum number ml, the angular momentum has the magnitude ml h bar. Okay, and so the magnitude of this arrow is ml h bar. So that means we can calculate how big the angular momentum of this particle is once we know the wave function of the particle. All right, so that's great. That is one step closer to the atom. But as we already understood, ring-like motion is nothing like motion of the electron around the nucleus, because that is going to be three-dimensional. So we have to consider motion on a sphere, not so much on a ring. So we have to move this to 3 dimensions, or in fact, 2 dimensions first, because we're going to only consider the motion on the sphere and not as a function of the distance away from the origin. So not as a function of r, but of the angles that define the sphere, which is going to be theta and the same as the angle we just talked about, which is phi. So theta and phi are the angles that fully define the sphere here. And we ask ourselves, what is the motion of the electron on this sphere? Can we say something about it? Well, in the analogy here is the fact that the particle has wave-like properties. And we know that if it has wave-like properties, we will get standing waves if the electron is to move along the sphere, okay, or on the sphere. So what we expect is something like this. We expect a 2-dimensional wave, a wave-like pattern that is projected onto the spherical surface, okay, as is shown over here. This is just one realization in which I can have a standing wave pattern that is projected onto the spherical surface. So think about the 2-dimensional wave that we found in the box, the particle in the box. We had maxima and minima, right? 2-dimensional particle in a box, but now it's not in a box. It's not in a 2-dimensional box. It's on a 2-dimensional spherical surface, but the same conditions hold. There are boundary conditions in such a way that the wave function can only be single valued at each position. That means it must replicate itself on the sphere, okay, forming a standing wave pattern that repeats itself on the sphere. So that is what we would like to find. We would like to find what are standing wave patterns, or not only standing wave, in fact, what are patterns that are self-replicating on the surface without creating double values for the wave function, that we can now take as the solutions of this problem, okay? Because that's what we need to find. Those are the boundary conditions that I have to fulfill. So how do we do that? Well, we'll start by first kind of converting the problem from x, y, z into spherical coordinates. We need to do that, okay? We need to do that because the x, y, z coordinates are not really useful here. It's much easier to use theta, phi, that's the same phi as before for particle on the ring, okay, the motion in x, y, and r, which is the distance from the origin. So we will use the spherical coordinates, and that's given over here. X is in spherical coordinates in terms of r, theta, and phi, r times sine theta cosine phi. And y is r sine theta sine phi. Okay, hopefully you've seen that before. And z can be written as r cosine theta. So we have to make the conversion from Cartesian coordinates to spherical coordinates. And once we know that, we can now write the Hamiltonian in terms of these new coordinates r, theta, and phi. Okay, you don't have to do that, although you can. It's actually a lot of fun to do it, but I'm going to show you the result. The result is over here. So what I'm doing is I'm going to convert this del squared, which as you previously saw is dx squared, dy squared, and then dz squared, okay? That is going to be converted into spherical coordinates, okay? And the way to do that is this. This is the result. I get, of course, the constant in the front, minus h bar squared over 2m, which is always there. And then these derivatives with respect to x, y, and z are now with respect to r, theta, and phi. So the r component is given over here by the first part, between parentheses. That is the r part. And the theta and phi part derivative is in this thing, okay? And so we have to know what that thing is. What is it? Here it is. This little lambda squared, capital lambda squared, is called the Legendrian, and indeed, it has the derivatives with respect to phi and with respect to theta. And it looks pretty awful, okay? It looks pretty awful, this expression, but we don't care at this point. We're not really being flustered by things looking awful. These are just computations that in principle we can do. We don't have to worry about it, it turns out. I just want to show to you that these are real things, and it is actually not as bad as it looks, okay? So what we have here is the Hamiltonian in terms of the derivatives with respect to r, first term, and with respect to theta and phi, which is given right here by the Legendrian. Why is it called Legendrian? It's named after a person called Legendre, which is a mathematician and that lived a while ago in France. Okay, so that's why it's called Legendrian. He figured this out for the first time. Notice also that I have not considered any potential on the surface. So V for the Hamiltonian equals 0. No particular potential well or anything on the surface. V is zero everywhere on this surface. So what we're doing now is trying to solve the eigenvalue equation for the Hamiltonian, okay, for this condition where I now have the Hamiltonian expressed as the derivatives with respect to r, theta, and phi. But since we're only concerned with what happens on the surface of the sphere, not so much along r, we can basically say that this term is going to be 0 because we will not consider the motion along r. So no change along r, only changes along theta and phi. So the first term is going to be canceled out, and what I'm left with is basically this eigenvalue equation of the Hamiltonian. This is the wave function that I'm trying to find, only a function of theta and phi now. I'm trying to find the waves on the spherical surface, and that should give me the energies times the function again. This is, of course, the eigenvalue equation. So what I have is this operator, lambda, capital lambda squared, with this pre-vector. This r squared was in front of this lambda, if you wish, okay, from the previous page. Hopefully you can see that. This mr squared, of course, is going to be I, okay? That is going to be I later on. This is, again, my moment of inertia, right? So that's the pre-vector, h bar squared times 2, h bar squared divided by 2I. That's going to be my pre-vector. And then this is going to be the dependence only on theta and phi, the r dependence we're not considering here. That is the condition that I'm trying to solve to find what are the wave functions that fulfill this eigenvalue equation. First things first, I'm going to move this prefactor to the other end, okay? So this whole thing is going to go whoop right there. So that results into the following equation. The operator, once again, operator with two derivatives, theta and phi, theta and phi, sorry. And that's the wave function. And then the prefactor here now, which contains the energy and this 2I over h bar squared. We've seen this term before. Okay? This is the same term that we had for the particle on the ring. Remember that? Okay, so how can we solve this? Okay, this is a pretty gnarly operator. This lambda, this Legendrian, is pretty gnarly. So this is going to require a little bit of effort. Now, good thing is, of course, that we don't have to do that on our own. These solutions are well known. So let me discuss with you what these solutions look like. The solutions are called the spherical harmonics. Okay, these solutions have a name called spherical harmonics. It's a very general solution in mathematics, very important solution, in fact. Okay, so we write this as capital Y, L, comma, ML. Now this ML is exactly the same as the ML for the particle on the ring. Okay, because the ring is part of the sphere, so that hasn't changed. But there's a new one, which is now L. Okay, there it is. That's the new quantum number. So the spherical harmonics, remember, is a function of two coordinates, theta and phi. And so it has two quantum numbers. Okay, that's important. Two quantum numbers because there's two dimensions, okay, theta and phi. The first one we already know, that's ML, that is the quantum number along phi. That's the same one from last time. And the L is the new one. The L has to do, of course, with theta, the quantization along theta. But as we see, the quantization along theta depends actually on both. So here it is. The function y, the spherical harmonics, has two parts. The first part is this part. That is the solution for the particle on the ring. That's exactly the same solution we found before. Okay? No change. That's the same thing. But in addition, there's a second part, and that is capital theta that now depends on L and ML. So the capital theta depends on two quantum numbers and is only a function of the variable theta. All right, so together they form the solutions to the eigenvalue equation above. And the solution is called the spherical harmonics. Now, what about this L and ML? Are they related some way, somehow? And the answer is yes. Okay, L is again an integer. Okay, the integer that labels the solutions of the wave function. It starts with 0, then 1, 2, 3, all the way to infinity. ML, which previously was any integer value, remember that? For the particle in the ring, but now ML is not just any. ML now depends on whatever L is. So when ML is part of the spherical harmonics, its value is not arbitrary. Its value is actually slaved to whatever L is, okay? So these two quantum numbers are now related to one another. The quantum number L is called the angular momentum quantum number, and the ML is actually the angular momentum projection operator, a quantum number ML along the z-axis. We'll see what that ML actually means, okay, in a moment. So what do these functions look like? Because this is still very cryptic, okay? So let's have a specific example. So here it is, the lowest possible solution, the lowest quantum numbers L and ML are called 0, 0. Okay, those are the lowest ones. Is this correct? Let's find out. L is 0. Okay, that means that ML, sorry, is now related to whatever L is. And L runs from, ML runs from L in integer steps to minus L. So whenever L equals 0, the only possible solution for ML is 0. Okay, there's no other one. So the lowest possible solution, therefore, is L, ML, which is 0, 0. And in that case, the solution for the spherical harmonics is the following. It's just a constant. That's easy. So it's just a constant on the sphere, which means this is completely spherically symmetric. Completely spherically symmetric. Everywhere on the sphere it has the same amplitude. The next one is when L equals 1. Okay, when L equals 1. Now, what are the values for ML when L equals 1? Let's count it. The highest possible value is 1, and then in integer steps to minus L, which is going to be minus 1. So that's going to be 1, 0, and then negative 1. So there's 3 solutions for ML. So whenever L equals 1, there's going to be 3 valid values for ML. And they're going to be 1, 0, and minus 1. So here they are. L equals 1. There's several values for ML that we have to consider. First, 0, and then the plus minus 1. And the solutions look a little different. When ML is 0, you can see it is a constant times cosine theta. And when ML is plus or minus 1, then I have 2 solutions with different signs, where it is a constant times sine theta, and then the complex exponential. Now, the complex exponential is, of course, this part is that thing. Okay, that's the particle in the ring. So that's the contribution from capital phi. And the capital theta is contributing the sine part and the cosine part. All right, so this solution here only depends on theta, but this solution here depends both on theta and on phi. Okay, so they have different kind of characteristics, if you wish. So these are the lowest order spherical harmonics, and we will see this has tremendous application. Okay, these actually have already a lot of the character of what we know about orbitals. Not everything yet, because we have not considered the R dependence. This is just standing wave patterns with or without angular momentum on the surface. Okay, we have not considered any quantization along the distance. That is for next time. Okay, when we consider the atom, but this gets us really close. This is where the shape of s and p orbitals and d orbitals come from. It comes from the fact that you have to fit a wave onto a spherical surface. And the waves will be quantized as before. They form patterns on the surface, and these patterns correspond to the shape of orbitals. Okay? this is where it comes from. And you can see it is completely mathematical. We can completely determine what these shapes look like. Okay, so here, let me just show you what these things look like. Here is the lowest possible spherical harmonic, when L equals 0, and ML, of course, is also 0. It is spherically symmetric because it's a constant on the surface. It's the same everywhere. This would mimic the situation of an s orbital. So whenever L equals 0, we are dealing with an s-type orbital. When L is 1, we know we can have different values for ML, namely -1, which is the one over here, and then 0, that's the one in the middle, and then -1, that's the one on the right. So there's 3 different versions, okay, of the orbital with quantum number L equals 1. These are the p orbitals. So there's 3 p orbitals. They are degenerate, as we will see. They have the same energy, but they have slightly different shapes in terms of the wave function itself. So 3 wave functions, same L, different ML, same energy, but different shapes. Those are the 3 p orbitals. These will be the d orbitals, okay? Remember, these are not exactly the orbitals yet, because we only consider theta and phi. We don't consider quantization along R. That will be for next time. L equals 2. Now there's 5 solutions. ML is running from 2, 1, 0, -1, and then -2. And you can see the patterns on the sphere. They become more and more complex. There will be more nodes on the surface, as you can see, because we create higher order wave functions. That means more complex patterns, more nodal planes will be introduced as we go along. This is L equals 3. Now there's going to be 7 solutions, okay? -3 for ML, -2, sorry, 3, 2, 1, 0, then -1, -2, -3. So a total of 7 orbitals with L equals 3. Okay, and we can go on if you want. This is L equals 4. Now we have a total of 9. 9 different realizations of the ML quantum number. So you can see that we have standing wave patterns that become more and more complex on the surface. I say standing wave, but technically the only real standing wave solutions are the one over here, where ML in the middle is always 0. And if we go to this side and this side, I have ML values that are not going to be 0, and it turns out they have angular momenta. That means these patterns, even though they look like standing waves, they actually spin around. That's one way to think about it. Okay, this one spins to the right, this one spins to the left. So that is, these have angular momenta. The middle part has not angular momentum. Truly a standing wave. Okay, so what are the properties of these wave functions? Now, this looks like a pretty scary expression, but what is it? It really is simply the integral over the product of 2 of the spherical harmonics, okay? So this is just basically the situation of having 2 eigenfunctions and multiply one with another one and integrate over the entirety of the relevant space, which in this case is integration over the surface of a sphere. And if I do that, I have to integrate over phi and over theta. Theta is running from 0 to pi, and phi is running from 0 to 2 pi. So those are the integration boundaries to basically span the entire sphere. There's also this term, the sine theta, which is called the Jacobian term. You have to include it, otherwise you will not be doing the integration correctly. So this whole thing is my integration factor. Okay, so that defines the integration. And then these 2 are just the multiplication, the product of 2 of the eigenfunctions from the set. Remember, the spherical harmonics form a complete set, just like we've seen before. Okay? These are solutions of the Schrödinger equation, thus they form a complete set. And if I do this product, integrate over the entirety of space, then I must find something like this. If they are an orthonormal set, that means that this integral is only going to be 1 if and only if both ML and L are going to be the same for both functions. Okay, so that's what these Kronecker deltas say. They say ML must be equal to ML prime and L must be equal to L prime for this integral to be 1. Otherwise, the integral is going to be 0. All right, so that's the same condition as before, same condition as before. And one way we can write this, maybe a little cleaner, is this, the bracket notation, okay? The new notation that everybody hates in the beginning, but later on realizes, wait a minute, this is a lot easier because look at this integral, it looks a lot cleaner. What I retain here is only the relevant values of L and ML. Those are the only things that fully define the shape of the wave function. L and ML define the shape of the wave function, okay? And I'm going to take the integral of the two. One of them is the bra, the other one is the ket. And this must equal the same as above, of course. So the Kronecker delta ML, ML prime, and then the Kronecker delta L, and then L prime. Okay, so this shorthand writing here of the bracket notation is actually very convenient for recognizing, symmetries in these computations. Okay, so instead of writing this whole thing out and you get easily confused and you make notation errors, this is a much cleaner way of looking for when is something going to be 0, when is something going to be 1, what are things that actually contribute to my calculation and what are things that don't. So that's why this is going to be very helpful as we move along. Okay, so let's look at the following. Okay, so this is now the operator, the Legendrian, operating on the solution that I just found, the spherical harmonic. The question that we haven't addressed yet is, what are the eigenvalues of this wave function? Okay, so what are the eigenvalues of this wave function, this guy, the spherical harmonic, when the Legendrian is operating on it? And it turns out the eigenvalues are this. Okay, it's minus L and then L plus 1. Okay, minus L times L plus 1. That are the eigenvalues of the Legendrian, and the eigenfunctions are the spherical harmonics. All right, now this is very close to the energies that we would like to find, because remember, there was a prefactor here in front for the Hamiltonian. This is just the Legendrian, and there was a prefactor here in front. And so what we can say now, if you conclude a prefactor, which is 2I over h bar times E, okay, that was the prefactor before for the eigenvalue equation of the Hamiltonian. That was the one for the Legendrian. So that means these two things are going to be the same. And that means now I can write this in terms of the energy. And the energies that I find are quantized, okay? Here it is, L times L plus 1, and then times this prefactor once again. So the energies for the wave functions on a spherical surface are, as expected, quantized, and they are quantized according to this formula. So whatever L is, you're going to have a specific energy. Note that the energy of the wave function, of course, is a spherical harmonic. That's it. That is the wave function. Only depends on L. It does not depend on ML, as you can see. So the energy only depends on the angular momentum quantum number L and not on ML. Okay. Okay, so what can we say about this? How can we compare this actually to the classical formula for the energy? And let's look at the following. Classically, the magnitude of angular momentum, and this is something we have already introduced, is I times omega. Okay, and we can indicate that by L, big L. So that's the magnitude of the classical angular momentum, I times omega. So quantum mechanically, I can now do the following. I can write, this is still classical, by the way. This expression is still classical. This is the L squared over 2I. That is the classical energy, okay, the classical energy due to spherical motion. That's given over here, L squared times 2I. But now my angular momentum is quantized. In fact, L is equal to this. So if I compare the formula that I just determined, this one here, with this one here, this is the classical formula. The second one is the classical. The first one is the quantum mechanical. You can see the only difference between the two is the h bar and this factor. And therefore, L squared can be computed. And L, therefore, has this value. Okay? So that means that the angular momentum, the magnitude of angular momentum of a particle that moves on a sphere is this expression. That is how big the angular momentum of the particle is. That means the angular momentum, of course, like the energy, is quantized. and it depends on L. Okay, so if you have a particle that moves around on a sphere in the quantum mechanical world, that means that you will have two things that are quantized. You have quantized energies and you have quantized angular momenta, and that is given over here. Okay, so what about this operator LZ, the one we just introduced at the beginning of this lecture? What if operator LZ is operating on this new function that we found, which is the spherical harmonic? And remember, the spherical harmonic is the eigenfunction for the Hamiltonian that describes the motion of the particle on a sphere when V equals 0 everywhere. Okay, so LZ is what we found for the particle on the ring. This is going to be the magnitude of angular momentum pointing along the z-axis, right? So what happens if I operate now with this guy onto this spherical harmonic? So that's basically written over here. I'm going to write out the spherical harmonics in terms of this capital theta function and capital phi function. And I know that LZ only depends on the variable phi. And the only function that has actually phi dependence in it is this guy. So that means I can now move this LZ over. It does not operate on a big capital theta, and only operates on capital phi, because that's the only function that depends on phi. Okay, so that means that I can now operate on this function, but this function was exactly the same as before. This operation we basically just did a couple of slides back, and the answer was MLH bar times the function again, right? So that means that I retain the spherical harmonic, and that means that indeed the spherical harmonic is also an eigenfunction of this operator LZ. There it is. The magnitude is ML H bar once again. So whatever the value of ML is for the spherical harmonic, that is going to be the magnitude of the projection of angular momentum along the z-axis. This is the shorthand writing in bracket notation. LZ operating on a spherical harmonic, which is now only defined through its quantum numbers, L and ML, that equals ML H bar, and then a function again. So the magnitude of the angular momentum projected along one of the axes, in this case Z, is ML H bar. So whereas on the previous slide I just said the magnitude of angular momentum depends only on L, but the projection of this magnitude along one of the axes, in this case Z, does depend on this quantum number ML. So the ML quantum number is the so-called projection quantum number of the angular momentum. Okay, it's also called the magnetic moment quantum number. Right, the magnetic moment that results from angular motion of a charged particle, and it has projections along Z, and that is what ML means. So ML is a projection of angular momentum. L is the magnitude of angular momentum. And we'll be more specific about this as we go along next week to understand motion on the spherical surface and also along R. What I'd like to end with is just an example to kind of show you how relevant these results are. You probably recognize already the similarity between the solutions of the spherical harmonics, wave functions, and the orbital shapes, okay, the S and P and D orbital shapes, and they have a really strict relation between spherical harmonics. Not exactly, but very close. But now I'm going to show you one that can be solved only by considering the spherical harmonic, and that is the so-called rigid rotor. Okay, let's consider a molecular diatomic. Previously, we considered the relative motion between the two, vibrational motion between the atoms. That is a harmonic well, remember? It's a harmonic energy potential. But now we're going to consider the spinning motion of this whole unit. Okay, so that's called a rigid rotor. I'm just going to imagine now that this stick between them is stiff. I'm not considering the vibrational motion. I'm just considering this little dumbbell, and I'm asking myself, in which ways is this dumbbell allowed to spin? That sounds like a silly question, because classically it can spin in any possible way. It can spin in any possible direction. But quantum mechanically, the spinning directions and the ways in which this rotor can spin is restricted because of quantization. Okay, so let's see how that works. So this is the kind of the schematic that we should keep in mind. I have two masses, M1 and M2. Those are the two atoms, and they will spin along. And let's say to make it easier for myself, I'm going to draw one axis, and that defines a spinning motion. But this axis, of course, can rotate. So this whole rotation can take place in many directions. But we're going to ask ourselves, in which directions are we allowed to spin? Okay, so we can do the computation. What we have to do, and I will not go into detail, it's actually in the notes once again, but we can do a separation of variables of the overall mass of this unit. So the center of mass, Cm, is moving through space. And then, of course, the relative motion within this unit is going to be able to rotate. And that's really the motion that we're interested in. So what we have to consider is not the mass of the individual particles, but really the reduced mass, and how the reduced mass is basically spinning, okay? So if we do that trick, it's called the separation of variables, we can actually study the way in which this rotor is spinning. And what we find is that this is really exactly the same problem as we talked about for the last 3-4 slides, okay? This is really motion on a spherical surface with no potential barrier. And so what we find are that the energies of this rotor are exactly the energies of the quantized spherical harmonics. This I was previously L. Sorry, this J was previously L. That was the quantum number L, but now we call this J, and this J simply means motion relevant to rotational motion, okay? Rotational motion of a rigid rotor. And so, but the expression is exactly the same as we've seen before. That means that the energies of this rotor are going to be quantized. Not every possible energy is allowed. This thing cannot spin in any other way, only in particular ways, okay? This constant here, B, is something you find oftentimes, that's called B, okay, in rotational spectroscopy. So if you look at transitions, and here are some actual transitions of molecular diatomics, it depends, of course, what the quantum number is. These are the states, the rotational states of the molecule, J equals 0, 1, 2, 3, 4. And then, of course, you can make transitions between the different states. And they can have several transition energies. You can express those energies in terms of this constant B, and then you'll find that the distance between 4 and 3 is 8B, the distance between 3 and 2 is 6B, 4B, and 2B, and so forth. So if you make transitions like this, you'll find a spectrum that looks like so, okay? 2B transition energy, 4B, 6B, and 8B. The separation between consecutive transitions is 2B. So this would be a rotational spectrum of a molecular diatomic, okay? So analyzed really with the help of spherical harmonics. Now, what is somewhat remarkable about this is if I ask myself, how does this molecule move in space really when it spins around? Okay, I know it has quantized energies, but how do these quantized energies relate to actual motion? Well, one way to analyze that is to operate with this projection operator Z, okay, on this wave function. So let's say the wave function again on spherical harmonics. It depends only on theta and phi. Oops, do it like so. And what I find, of course, is ML again, H bar, okay? And so what that means is that the projection of this motion, spinning motion, onto one of the axes, let's say Z axis, can only have certain values, ML, okay? So that means that it cannot spin in any possible way. It can only spin in a way such that the projection of that angular momentum of spinning onto one of the axes, one of the Cartesian coordinates, Z, has fixed values. Not just any orientation is allowed to spin. Okay, so let's say it can spin in this way and in this way, but nothing in between. So the motion of this thing is really confined. As soon as you pick an axis, okay, of this molecule, as soon as you pick and fix one axis and you project this molecule onto that axis, it turns out it can only spin in definite projections. Okay, so that is remarkable. Okay, that is of course strange because classically that is not the case. Classically, this molecule can tumble and move in any other way, but in this case, as soon as it behaves quantum mechanically, it can spin only in certain directions projected along the z-axis, right? So that is definitely a remarkable difference between a classical rigid rotor and a quantum mechanical rigid rotor. The fact that you see only discrete transition energies means that the molecule is only allowed to spin in a certain amount of ways and not in any other way. Okay. Okay, so there's a quick question. What are the two variables after the large phi at the bottom again? These two variables, this is little phi, this is little theta. Those are the variables that define the sphere. Okay, so the sphere, of course, is again this thing here. So I have an angle phi, that is phi. So around the circle is phi, and this angle in this direction here up is called theta. So those are the angles that fully define the two-dimensional surface. Okay, and this thing here, the rotor, this orientation of the rotor and the spinning is fully defined by the angles theta and phi. So this is the problem that's identical to solving the problem, the Schrödinger equation for the two-dimensional problem of a spherical surface. Okay, so that is it. Let me know if you have any questions about this material. Okay, this is the last material that we will be considering before the midterm, because after the midterm, we'll be focusing solely on the hydrogen atom. So this concludes the basics of quantum mechanics, the first part of this course. All right, so let me hop in. I see a question here in the chat box. It says, even though the exam is open notes, will we have an equation sheet just to have them all in the same place? There is a sheet with constants that will be provided. And you know, I should probably also provide a sheet with some formulas. So let me do that. So you have them all in one place and you don't have to look. So yes, the answer is yes, and I will provide that sheet for you. And I will actually post that sheet also before the midterm, so you can see what are the formulas that you have right there on the screen with you. So you don't have to guess which formulas will be given and which ones will not be given. Remember, this exam is not about memorization. It really is about understanding the material, seeing the relations between the different type of motions, knowing the difference between classical motion and quantum mechanical motion, knowing what quantum numbers are, knowing what wave functions are. By now, you should have a good feel for what a wave function is, knowing what an eigenvalue equation is and how you can calculate the energies once you know the wave functions, and knowing what operators are, and they have some interesting behavior, and you should be able to interpret that. Yes, the sample quiz answers have been posted. Okay, so you can check that out. What is the difference between the large phis on both sides of the equation on the bottom? There is no difference. Okay, this equation right here, okay, is the same as we've done a few slides back. This is basically the motion for the particle in the ring. Okay, so that's the same one. Well, maybe I should do it differently. Let me say the following. I was a little bit too quick there. So let me do it like this. L operating on the spherical harmonic Y. Okay, that's really what I wanted to do. But what I do, of course, is when I write out Y, what I'll see is that the Y has two parts. One is big theta, which only depends on theta, and then the other one is big phi, which only depends on phi. And what I'm doing here, this is the solution. Y is the solution of this problem. Okay, that's the spherical harmonic. This LZ, of course, is only operating on the second part of the spherical harmonic. That is this capital phi. Okay, that's the only thing that matters in this case, because only this variable phi will determine the motion of the particle in the ring, which determines the projections along the z-axis. That is it. It's not theta, it is phi that determines that. Okay, so that is why I wrote only capital phi. It is the particle of the ring part that defines the motion of the spherical harmonics. So I should have done that differently. I apologize for that confusion. Okay, so this above here is a better way to say the same thing. All right. Any other questions, folks, before we close?
I'm sorry, could you go back to that last page where you were explaining?
Yes, I can go back if you want. Here it is.
Thank you. I just needed to write
That's
everything
right.
down.
Sorry. Did you have a question, or you just wanted to kind of write things down?
I just wanted to write things down. I could take a picture of it though.
Okay.
Thank you.
So on this slide, on the bottom equation on the right side, one of those variables should be a theta. That's what people are saying in the chat.
Oh yeah, I see what the problem is. Okay, sorry. You know, yeah, I have an issue with these pens. You know, I would say, you know, forget about this. Okay, this should be a theta indeed, but consider just the situation above. So I should really write it like this: ML H bar, and then Y L ML, and then it's going to be so like this. Okay. Whoa, this is really stocky. Any case, it's ML H bar times the spherical harmonic once again. Okay, so whenever LZ is operating on the spherical harmonics, remember those are solutions of this problem, and what I'm getting is the answer of the projection of angular momentum along the axis Z, and that only has fixed values. That was the point. So forget about this kind of notation here. Something went wrong there. This should be a theta, and actually I shouldn't have written theta there in the first place. This is the correct way to understand that problem. If I would have my iPad, I would just take my eraser and erase this and do it again. But basically, the answer is written up here. Okay, it basically says whenever the projection operator angular momentum is operating on my solution of the wave function, I'm getting fixed values that depend now on ML, and that means that depending on ML, the rigid rotor can only move in certain fixed positions. That's one way to interpret this. And there's positions on quantized according to ML. That is the point. So forget about this crossed out thing. I think it led all into confusion. And in fact, I should have been more careful in writing this down.
Well, it makes so much more sense now. Thank you so much.
Sure. All right. Thank you, guys. Let me know if you have any questions about the midterm. You can always send me an email. If you want to meet with me privately and ask some questions, let me know. We can still do that before the exam. If not, good luck with the exam. Make sure you find all the information on the website, the solutions to the practice problems and the worksheets, so you can be prepared in a proper way.